Okay, we have looked at categorical data, and in categorical data, in past lessons, categorical data, we saw that we could do certain types of graphs, such as a pie chart and a bar graph. But those two graphs are not appropriate for quantitative data. And quantitative data consists of numerical measurements or counts. For example, discrete is counted because it takes on specific values, and continuous is measured because it takes on the values in an interval. So let's look at example 1 and think about what type of data is given here. We have the Ghost Shop already as a babysitting service in a mall. For a month, they kept track of the number of babies they were left with. So people just drop their babies off and go shopping. So it looks like on one of the days there was 31 babies, 24 babies. So this is counting the number of babies. So what kind of data do we have? We have quantitative, discrete data. That means it will not be appropriate to do a pie chart or a bar graph or a stacked bar graph. Any of those, that's not appropriate. So let's first put this data into our calculator and make sure we know how to do that. So let's go to our calculator. And here's my calculator. I have some data here in L1, and that's not the right data. So I'm going to go up to the top and I'm going to hit clear. If I were to accidentally hit delete, it would delete the entire column and I'd have to use second insert to get it back. But I don't want to do that. I want to hit clear. And there it is, cleared. And now I've actually entered this data into this calculator in, that's the right data in L4. So what I'm going to do is I'm going to go over here to L1 and I'm at the top and I say, could you please bring the L4, second 4 gets me the L4. So in L1, could you put L4's data? So let's see if that works. Phew. So there's my data I've entered in the list. You see in your notes, stat, edit, enter your data in the L1 list. And then it says determine the summary statistics. So to do that, I'm going to quit to get out of this. And I will hit stat, calc, and one of our stats. Now this calculator has the old software package, so I have to actually enter in what I want it to do this with, and I want it to do it with the L1 list. Yours software probably says X list, that would be L1, and then it says frequency list, and that's if you have a frequency table, but we don't have a frequency table, we just have a list of data. So you'd want to make sure that the frequency list says 1 or says nothing. Okay, so now I'm going to hit enter, and even with the new software, you should end up with this list. There's your mean. If you don't have 23.3, then you've entered your data incorrectly. Then we have our sigma, and so now I'm going to go back to the note page and start writing in what all these things mean, because you can see what the screen is. Oh, and if I hit the down arrow, you can see the second screen, which has the 5-number summary right there. So both of those screens are on your notes. So first thing on here, what is X bar? That is the mean. To get the mean, you added all the X's, added them up, and divided by how many you have. So this next symbol, that is the Greek letter sigma, and it stands for summation. So what this is saying is add all X values. And so you can see adding all the X values in our data was 699. And this is a capital sigma, by the way. Sigma. All right, next one, x squared. That is basically they squared each x value, then added these squares, found the sum of the squared values. And the reason why they do that is because it is used by the calculator to find the next term on here, which is this is a letter S with a little subscript X, kind of to tell you that remind you that you have a standard deviation. This is standard deviation of a sample. This is what you expect the sample to vary by on average in the same units as mean. So if it's number of babies, you expect on average each day, you expect 5.23 babies to vary by that from the mean. That's on average how much it does vary from the mean on a sample. Now, if you have a population, this is also sigma. This is a lowercase. And we use Greek letters to show population values, and this is the standard deviation of a population. N is the number of data values, count of them. Remember, we had 30 babies. The min X, that's the minimum number of babies in our data set. So that's the minimum value in the data. Then if we divide the data into quartiles, into groups of 25% each of the data, the number that separates the lowest 25% from the next 25% is called the first quartile. We'll be using that when we do box plots. Then we have the median that separates the lower 50% of the data from the upper 50% data. So yeah. So I'll put first quartile, that's the lowest 25% value separating. Okay. Third quartile, that value separates the top 25% of data. So third quartile separates top 25% of data. And then max X, that would be the maximum X value in the data. Okay, so now you know what all the terms in that data mean. So we'll go on to the next page where we will look at what we're going to, when somebody says that you are going to describe, what things are you going to say? So when you're describing data, you want to describe the socks. Knock my socks off. That is the shape, outliers, center, and spread. So first of all, the shape. What words will you use to describe the shape? First of all, this first shape, this one is symmetrical, but this one is also symmetrical as well. But a lot of times when people say symmetrical, they're talking about this shape right here. But this one is symmetrical bell-shaped, really. You just say bell-shaped. The last one, it's symmetrical, but it's also called uniform because you can see that each group is somewhat similar to each other. Even if it was something like this, I would still call that uniform because it's generally the groups are fairly similar to each other. Okay, now this shape right here with the tail is on the right side, we call that right skewed or skewed right, also known as positive skew. Then we have this next one where the tail is on the left. And so that one we call skewed left or left skewed. And that one is negative skew. I'll just put negative. So negative skew. And what's interesting about these is that if you look at, it's hard to read on the page, but in right skewed, the mean is going to get pulled to the right higher than the median. And in left skewed, the mean is going to get pulled to the left, which is going to be lower than the median. And outliers are going to be strange values that are different from the rest of the data, far away from the majority of data. Next page, we'll learn how to calculate this. To describe the center, you're going to give the mean and the median with units. In spread, you're going to give the standard deviation. Don't worry about giving the variance. Do give the range, max and min. If you feel like some of these other values are important, you can of course give them, but I would like standard deviation, range, max, and min. And then you may want to mention time if you see that there's some kind of change happening with time. That won't really apply to the problems that we'll be working on. So we look for major peaks, we look for clusters, we look for obvious gaps, we look for potential outliers, not just what's the smallest and largest observations. We look for rough symmetry or skewness, and there's a lot of variation in how people can describe their data. Okay, so to decide if something's an outlier, what's going to make something an outlier is if it's unusually high or low compared to the rest of the data set. So the first thing we're going to do is find the inner quartile range. That was from the 5-number summary, quartile 3 minus quartile 1. That's the inner quartile range, also known as the IQR. Then what we need to do is know what 1.5 times the IQR, what is that value? Because that value is going to get added to, that 1.5 IQR is going to get added to quartile 3. And if you are above that value, you will be considered a high outlier. If you have a quartile 1 and subtract 1.5 IQR, if you are below that value, you are considered a low outlier. This method always works to find outliers. And it is the preferred method for the AP exam. Another method that can look at if something's unusual, but only applies to what's called normal data with a capital N, is using the mean and the standard deviation. And in that method, you're using the mean and you're adding 2 sample standard deviations, or adding the mean and adding 2 population standard deviations. This symbol mu is the population symbol for mean. This method, though, and then looking at the low outliers, so it has the same sort of setup as it did with the IQR. The problem is this only works for what we call normal data. And I'm going to put a capital N on the normal. Normal data is data that not only fits the bell shape, in addition to fitting the bell shape, it fits into a perfect percentages of, well, not perfect, nothing's perfect, nearly 68, 95, 99.7% in the graph intervals. But we're going to talk about that later, so I'm not going to spend time on that right now, because you don't know how to find out if it's normal data. So that's why we're going to use this method, which always works, and that's going to be the method we're going to use to find outliers. And it's what the AP test wants, so that's lucky. Okay, next page. We have got our baby data still in our calculator. It was quantitative data. So what type of data? Quantitative. Meaning that a dot plot is appropriate. Dot plots are for quantitative data. So let's make a dot plot of this data. And what I find is, just as a things that you want to think of, is you want to make sure you have a title. You want to have a scale. What might be the easiest thing to do with the data in the calculator is, first of all, let's go to Stat, Edit. Wait, no, sorry, I didn't want to do that. Stat, Sort. Okay, I'm going to sort it ascending. And it says, what do you want to sort ascending? I say, well, let's sort list L1 ascending. Now I'm going to look at what list L1 looks like. And here it is. Look at how those numbers are now going up in ascending order. And that's going to make it easier for me to graph this on my paper. So you have this in front of you. I actually have it in front of me on a separate calculator. So first of all, dot plots are appropriate for discrete data because they are specific values. So here's my dot plot number line that I'm going to start. And why don't I go with 14 babies, and then 15, 16, 17, 18, 19, 20, 21, 22. So I'm just labeling 23, 24, 26. I'm going up to 32. 27, 28. Well, those 28. I'm going to have to make this longer. 30, 31, 32. Okay, number of babies. Okay, title, dot plot, plot of the number of babies. See how specific I am? Left at go shop already. Okay. Now let's put them on there. So from my calculator, I saw that there was 114. So this time I'm doing dots or X's, whatever you like. 16, There were 2. There were 2 at 17. There were 2 at 18, 19, and 20. There was 1 at 21, 1 at 22. There were 2 23s. There were 3 at 24. Trying to make the spacing good. 25 had 1. 26 had 2. 27 had 1. There were none at, that's 28, not 38, 28. There was none. 29 had 3. Also 30 had 3. 31 had 1, and 32 had 1. So there's my Go Shop Already babies, and now I've got to describe my shape, outliers, center, spread. Socks, okay? Because that's what it says. Describe the data. So when it says describe the data, they mean socks. So every time you start a description or do anything with data like this, I want you to make sure you have context. Okay, so let's start this sentence with what we're talking about. The shape of the number of babies left in the mall babysitting service See how I have context? That's context right there. Okay, so let's see here. The shape. What do you think of the shape? Bell shape, left skewed, right skewed, uniform, or something different? I would say it's about uniform because it seems like it's fairly level all along. But it's not perfect, is it? So approximately uniform or roughly uniform. With, well, let's see, are there any outliers? Let's find out. We know that IQR is Q3 minus Q1. So that is going to be 29 minus 19, which is 10. So my max typical value is going to be, let's see here. I'm going to just extend my page. Whoops, if I can. Okay. My max typical value, if I go 29 plus 1.5 times this IQR, which is 10, I get 44. And that's our max typical. So at 44, we would say it's not unusual. But at 45, we would say it's unusual. Were there any counts of babies over 44? No. So there were no high outliers. Because you never went above 44. Now let's check the low. So let's check the min typical. And min typical is going to be if it goes below the Q1, which was 19, subtract the 1.5 times the IQR with 10 again. So did it ever go below 4? And there were no values that went below 4, so there were no low outliers. So continuing what I'm writing with no apparent outliers. See, I had to check it though. So, okay, I've done my shape, I've done my outliers. Now let's do the center. So that's mean and median. The mean was 23.3 babies. In stats, we always report one more. So we want to report one extra place. than the original data in both the mean and the median if it exists. And the median was 23.5 babies. I'm just going to point out right now that the fact that the mean and the median are very similar to each other, 23.3 being only 2/10 different from 23.5, being so similar like that is more evidence that we have something symmetrical, which means either bell-shaped or uniform. So that's more evidence that this was symmetrical. Because the mean is slightly lower than the median, you might have been able to say slightly left skewed, but because the mean is below the median, you could not. The only answer that was definitely wrong was right skewed, because you cannot have it right skewed if the mean is lower than the median. So I would say that supports symmetrical in my mind. Okay, so I've got the center, shape, outlier, center, spread. The data varies from 14 babies to 32 babies with a range of, and range is actually the max minus the min. So what number is the max minus the min? Let's see, 32 minus 14 would be 18 babies. 18 babies. I don't know why I'm now writing in green, but the standard deviation is, now you got to decide, are you going to use the population number of babies or the sample? And this was a sample of just one time or like many days, but like it's not every single time ever in the world that was ever left at the Go Shop already. It was just a sample of it, so it's appropriate to use a sample value of 5.2 and the same units as mean, babies. And again, also appropriate to have an extra place. So there's that. So now we've done it. We've described our data. Now let's do the next type of quantitative graph that you could make. And this one is a stem plot. So here's a stem plot. Again, something appropriate for quantitative data. And so we want to decide if one of these genders is taller. Is it males or females? And stem plots are very good at helping us compare something like that, especially if we do like the back-to-back. And again, this is also for discrete data because you got to have individual points. And I've also entered this into my calculator. So I'm going to pick one of these, and I guess I'll just pick the males mainly because there's slightly less males, but I'm going to pick that, and then I'm going to draw this as a stem plot, and then I'm going to recreate it as a split stem plot and a back-to-back stem plot. So going in to do my stem plot. Back to the calculator, I have my data, and actually I'll put it in L1. My data for the men is in, I think, L5. Yep. Okay, so here I'll put it in. Okay, so L1 is now going to be the L5 data. Boom. And I'm going to stat sort to make my life easier. Do that to L1. Enter. And now stat edit. And now I'm going to make my stem plot. And again, I have this data on my calculator, so I can see it. Okay, so when you're drawing a stem plot, again, you need to have a title. So stem plot of male heights in UK. Now, the stem is the part of the number that's sort of you see repeating. I see the 150, 180. That's going to be the stem. So the lowest one I see is 150. So there's 150, 160, 170, 180. And then I look through and I say, well, how many? There's a 4, a 7, a 9, a 1. And then in a stem plot, you want to put them in order. So 1, 4, 7, 9. And you want to be consistent in your spacing. Then with the 160s, you look through, find all the 160s. And let's put those in order. So because 162, there's a 35, there's 2 of these 5s, so you have to write it twice, 7, 9. Notice how I'm being consistent with my spacing. And now on to the 70s. So 4, 5, 6, and 7. 0, 3, 7. And that's a stem plot, but it needs to have a key so that the reader can put it back together, and the key with units. Okay, so whoops, units. So that is going to be 1, 5, line 1, and the reader will know that that's 151 centimeters. Then, of course, you could describe your shape, outlier, center, spread. But and outliers, you check the 1.5 IQR. But I'm not going to do that right now because that takes a while. Okay, now I'm going to split the stem. And so basically to split the stem, you're splitting it into the groups of 0 to 4 and 5 to 9, sort of in the direction of what you'd do for rounding. So to split the stem, I take my stem and I just go 15, 15. So the 1 and the 4 go in the first group, and the 7 and the 9 go in the second group. And what this does is it just makes it a wider stem plot, and so it kind of spreads it out, especially when you have kind of a tall group individually. But so I've split that out, so I'm going to split out the 16s. And if any of the subgroups don't have anyone in it, you leave those blank. So now the 16s, there was a 2, a 3, 5, 5, 7, 9, 4, 5, 6, 7, 0, 3, and 7. Again, I need to have a key. It doesn't have to be the 15 one. I could do any one that I want. But as long as I have units and a title, so and then this says, oh, well, let's do a back-to-back plot with the female data as well. And so the way that works is the females are actually going to go this way. These are compared to the males' heights. You know, these are the males, and the females are going to go the other direction. So if you look back at the female data, in the 150s, there was a 2, a 3, and a 3. There was a 7, 8, 8, 8, 9. There was a 0, 0, 1, 3, 3, 4. There was a 5, 5, 6, 6, 7, 8, 9, 9, and then there was no one in these groups, so we'll leave those empty. And then if we wanted to compare, you have to use comparison words. So you want to use the number what you're comparing to, and you want to say it's blank higher, it's blank lower, it's similar. So if I'm going to compare the data sets, in this case, I would say that the female heights are clustered in the 150 to 169 centimeter values, whereas the male heights are more bell-shaped and spread out over the 151 to 187. Okay, the female heights are clustered in the 150 to 169 centimeter values and appear to be lower than the male heights that vary from, I don't know if you can see this, from 151 centimeters to 187 centimeters, and are more bell-shaped, because I think that the females just seem to be clustered and males seem to be bell-shaped. And then what you might want to do is compare the means for each group. For example, the female mean is about 7 centimeters lower than the males. The female mean of 161.5 centimeters is roughly 7 centimeters lower than the male mean, roughly the male mean of 168.5 centimeters. So words of comparison, you give the number that you have and the number you're comparing to. Okay, so that was stem plots, and I think what I'm going to do is I'm going to stop the video here, and I'm going to do a separate video for the histogram so that you feel like you can have a little bit of a break. And so stopping this one here.